holds a PhD by our university. Then he moved to UCL, to London with a postdoc, and now he's staying there. Right. He's going to talk to us about building streaming architectures. So I will do it.
So it's good to be back home. So the topic I'm going to talk about today is quite a hot topic when you go to Big Data conferences and when people talk about products, and it's how to build things that are receiving a lot of data and that data needs to be processed to get structured kind of information out of it, and how to be resilient, machine failures, resilient code changes, and resilient new versions deployed, and all of that being done without the user of that information. So the structure of the talk is very simple. So it is why do we want to do it, when do we want to do it, what do we want, what do we have to do it, and how do we do it. So first of all is why. So when you review the evolution of these big data platforms, starting from old times, 2004, Hadoop, so that time the fact of doing it. So when you review the first as a user, when you review the first products that we were having on the web, the fact that you were having some kind of recommendation was already enough for that service to excel on top of all services. So building this kind of information for users, like let's say recommendations weekly, was good enough. But at some point, competition is starting to emerge between different services, so the more and more it was more important to have the right piece of information, put the right piece of information in front of users at the right time. So the more and more people were thinking, how can we, so a weekly recommendation, a stack weekly recommendation for someone is not good enough. You have to actually do by the minute. And actually, as the user is clicking, you have to update it. And maybe the weather is changing, so we have to update the recommendation because the weather is changing. So it's all of this becomes a set of feeds that is coming to the system continuously to react by the minute. So let's put an extreme example of so building streaming applications is kind of a trade-off between time and value. So you think about this when information is only valuable when it is by the minute, when it's by the time you need it. Once the time is gone, even if you do it, there is no value on the information. Let's think about a stream case about that. Let's think about a casino. So a casino, so the bank always needs to win. So a casino is, you can imagine, is monitoring all the people who is gambling in there by the second. And if they detect anything, they have to detect it while the person is there. So they have all sorts of complex systems to react to these kind of things on time, because if you don't react on time, what could actually happen is that by the time you react, the guy is gone. So the value of the information that the guy has secured is useless. So if you don't react on time, they will actually tell you should have done a streaming application. Another environment where streaming uses streaming data and give the data and tick data by the minute is trading systems. So it doesn't matter if the analysis you provide for trader is the best of the world. If it's not in the right time, there's no value of it. So first lesson about batch, the duality between batch systems that take petabytes of data and at some point provide the information, and streaming is time to value. So we think about streaming when the value just goes down with time pretty quickly. So if we have a kind of application where time is not the most important thing, and we can wait an hour or we can wait half an hour to get results, then we shouldn't be thinking about streaming applications. But if we are here, actually, we shouldn't be thinking about batch applications probably. So the next question is when. So when you see talks now in the internet and conferences about streaming, it's like kind of the flavor of the month. So now it seems that Hadoop is dead. All kind of batch systems are dead. Google is saying they don't use MapReduce, but actually, I don't think one thing is going to substitute the other. So, why? Because actually, it is harder to make it right. It's much harder to make it right a streaming application than make it right a batch application. To give examples, for things like counting or keeping a set, we start having to use probabilistic data structures and make all sorts of tricks to be able to cope with the traffic as we go through the stream, which things that we don't need to think when we are doing batch systems. And actually, most of the frameworks, and I hope we can see a couple of them before the talk ends, provide more or less the same API for doing a streaming and batch. So when you talk about a map, when you talk a flat map, actually coding one or the other is not much different. So you would better off probably starting by building the first version. If you're trying a new idea or you're trying a new service that you want to provide, you're better off providing it in batch probably, so you don't start by the minute, but you test it out. And then move to streaming once the requirements have grown and you need to actually do it by the minute. So as I see it, streaming is not always practical, and I think that there is 3 scenarios you can find. So there is a scenario where it's going to be mandatory. So if you're thinking about a trading system, it's going to be mandatory at some point. You know that it's going to happen. So when you think about this idea, you better think with the streaming in mind from the beginning. There is times where it's doubtful, and that's the situation where you're better off building a batch application first. That maybe it only updates daily. And once you have proven that the system actually gives some value to the people who is going to use it, then you move to streaming, which is going to be a bit more harder, but it's going to give more value. And there are situations where probably will never be necessary, even if they advertise that streaming is good, it probably will never be necessary. So, as I said, trading systems, one example where streaming is going to be mandatory, data has to go by the minute. Doubtful systems, so I gave the example of recommendations in Amazon. So now I'm sure it's going through streaming, but I'm sure at the beginning they were not doing it that hard because they were the first ones doing this kind of service. And I'm sure they started off by doing it daily or doing it maybe weekly per user, and then they move to more and more complex situations. I'm sure Facebook does many processes still in batch and some tweaks on streaming. And for example, in news agencies, when they decide a front page, they decide a front page daily. So that could be a very complex analytics, but you know that you only need it for the next day. So you have one day to compute all the analytics to do the next release of the front page. And maybe you can go one step further later and say, okay, now we are doing it by the hour. Maybe I have 3 different front pages during the day. So we're reducing more and more the time to compute. So we move more and more to the case of streaming. An example where probably it will never be necessary to do streaming is with politicians, right? So I'm sure these people have a lot of information, have to process a lot of information, but I doubt a lot that they are using information at the pace this guy is using information. So probably public services is a place where streaming will never actually excel because all the decisions are much more slower. So there's no point on doing something by the minute when it's going to be used monthly or be released by the quarter. So there is probably that's an environment that will never be used. So next question is what to do. So how do we organize a streaming application? So when we think about building a GUI, we have model B controller where we're thinking about microservices. We know there's persistence, there is service, there the resources that look to the outside. So what's the paradigm on streaming applications? So most streaming applications are built of 4 parts. First part, it depends on what the thing you're building, but it's basically getting the data at some origin of it. This data has to usually ends up in a brokering system that can be persistent or not persistent. So the definition of a persistent will be a queue that is keeping that until it is acknowledged that it has been processed and is not needed anymore. A system which could be not persistent could be, for example, Twitter API, which by the time Twitter has, so it just gives you data by the minute. If you don't consume it, the data is gone. You cannot come back and go to that brokering system to get the data again. Then all the data has to flow through a processing or analysis pipeline, which is usually designed as a DAG, as a directed acyclic graph of transformations from the data which is flowing to different places where you want to process it and to want to produce it for consumption. And the last stage is usually a sync. So once you have done analysis, there is usually a use case you are thinking about. So maybe you just put that in a DynamoDB or in an HBase for a web page to consume it and people to query it. Or maybe you can even come back and put it in the brokering system again, because maybe what you want to do is create a feed of data, a refined feed of data for other people to build services on top of it, maybe even internally. So you have different teams, and one team is actually using the feed of the other team, which is producing continuously. So there has been a lot of talking on how to organize things, and there is 2 main ideas. I think it hasn't been nailed still. So I think we are still exploring what is the best way of doing things. First idea was the Lambda architecture. So if you imagine more or less what it would be like to be doing something like this, you will have a release which is feeding data all the time and putting data outside. And you maybe want to change, at some point you want to do a new release of a new process. So, and people is consuming that, is consuming the latest, which is being produced. So you have a speed layer which is taking the latest data and is processing the latest data, but people usually want to come back in history a little bit, so that has to be a persistent data. So the idea these people had, I think, the origin was in Twitter, is you have a streaming system which is taking the latest data, and you have an equivalent batch system which is doing the same calculation. And when someone does a query, you merge both systems. So maybe you are consulting the last hour, and that comes through the speed layer, has been just processed 1 minute ago, but when you go back in history, maybe 1 day ago, you're actually querying the other layer, which is persistent, is already in a database, and it has been produced in a batch way. And the idea is that you're running all these processes all the time. So if there's ever an error in the code or a new release of the code, a new batch process since a new batch process is periodically being executed, the new analysis will be applied to all the data. And on parallel, the new data is also processed with this new version of the analysis in real time. So everything keeps synchronized, and nobody notices it that you changed your neural network or you changed your set of rules or whatever. But it's quite inefficient, because you're basically telling me I have to be batch reprocessing, for example, as Maria was saying, the last 6 months of the data for the user page to be fed. I have to be doing all that. That's actually money. That's actually machines you have to be running all the time, and you will have to maintain it. And the second main problem is you're actually maintaining 2 code bases. So you're telling me I have to have a code base which is the streaming API, which is one program, and another program which does the same thing. 2 things have to be synchronized for the thing to be coherent. And we have to make sure everything is synchronized and everything is running in sync. So that's kind of an inefficient, it's not a very good way of organizing things. So the second idea is, and we will see there are queue systems that are, so the idea of this is the speed layer is something that doesn't take much resources and is just for the latest data, and you have a huge repository which you can always take and create a view from it. But actually, modern queue systems are powerful enough to maintain a huge amount of data. So what people started to think is about a new kind of way of doing things. So how can we manage a change in a code without having to have two code bases and just having one code base, which is only the streaming one? So they will say, okay, there is a new release of a new pipeline that we have created. Okay? And so what we do is we keep the production one, and the data is flowing in this queue, and we create a parallel queue where we just take the batch data that is in the repository and we just put it in a queue as it was arriving today. And we just put a new pipeline and we are creating temporarily catching up with the production data. But this is, you just do this when you want to do a change. Once this queue has catch up with the latest data, it has consumed all the data, you just get rid of the old pipeline from production and you just plug in the production pipeline with the latest data, and things just change without having to have this batch layer which is doing this in parallel and only having one code base. And just by using the capability of the modern brokering systems like Kafka, which have as much power as an HDFS to actually store and maintain data. So this idea was called, I don't remember by who, I think it's some guy called Klefman, I think, Kappa approach, which is basically only maintain one code base, which is the streaming, make new releases of it, and as I said, just use the brokering system to make the changes. So that is basically the idea of it is not a set of tools, so it's just a set of architectural ideas, and it can be built with different libraries. It doesn't need, there is no library that does the whole thing, and that's part of the problem that makes things hard nowadays, because there's no one system. It's just putting together different systems to do everything. So at this point, we come to the how. So this part of the talk is more a tutorial, and I've kind of prepared small live demos of everything, but as with live demos, they can go wrong. So I hope we get we'll go through some of them. So first thing that happens when you say, okay, I'm going to do a streaming application. So you go to Google and put streaming applications with data. And the first thing that happens is everybody's trying to sell the system. So what you will find is that they call the same things. Everybody calls the same thing in 20 different names. And it seems that all the systems are different, and there is no kind of solid foundation. But in the end, actually, everybody's doing the same. So everybody has the same set of problems, and everybody's more or less solving the same thing. They are just calling in a different way, but it's just a matter of marketing. It's not a matter that there are different problems with different systems. So step one, how do we abstract a piece of information in a streaming application? So it is divided on 4 parts. The first part is so we produce messages all the time, and it has this. It doesn't matter where the message comes in. It usually has the same structure in all the systems. Which the first thing is inside the system, where is this thing going? So Kafka calls these topics. So which is the topic this thing is going in? Second part is, since we want to scale, we need to have some kind of sharding capability. So we have a partition key which we're going to use, is a piece of information we're going to use to say, okay, this goes to partition 1, 2, 3, and it doesn't matter the topic, it doesn't matter how many data is going in. You can always make more partitions of a topic, different machines, the thing scales up. So the partition key tells the producer who to talk to. There's some systems, there's always kind of a sequence ID. So the sequence ID is when you have group data, maybe, for example, let's say you have chosen in a partition, as a partition key the user ID. So all the data from the same user arrives to the same node. So the sequence ID can help, is the next bit that helps you to say where is the ordering. Does this go before? From all the stream from this user, what is the ordering of the messages that is arriving? Because that's maybe important for the process you want to do. And the last piece is the data. And data can basically be anything. So all the systems are coded in a way that the data is basically a byte array, and you just need to have a serialization process. It can be, so it can be a JSON, it can be Avro, it can be XML, it can be anything. You're basically, that's where you start building your application on top of the abstraction. Step 2 is hashing. So when you're a student, they tell you, okay, you do hashing to avoid collisions between things. Okay, big data hashing is the other way around. You do hashing to collide the things you want to be in the same place. So you basically, to decide an easy way without needing to orchestrate anything that helps you to decide where a message from a topic, for example, can go in, is just basically do a hashing, and if you have 10 machines, you just say, okay, that hash modulus 10, the number of machines I have, this is the machine I have to talk to, and it is repeatable, it will give you the same machine, so you ensure all the data from that user will arrive always to the same place. Step 3 is fault tolerance. So I had a colleague which told me once, and I like the sentence, distributed computing is parallel computer, but when you cannot trust anything or anyone. So you cannot trust the code base that has been released is okay. You cannot trust the machine is going to be alive all the time. Machines are going to die, and you have to keep the party going. So how do we cope with persistence? So you can imagine that to cope, let's say data is coming through a pipeline. That pipeline is made of 20 machines, and one of those machines it just basically died. And once he has consumed part of the data from the stream. So if that brokering system is not persistent, what's going to happen is that data is going to be lost because there is no way of coming back. But if it's persistent, I can always raise a new node, a new machine, for example, and this new machine just takes it from where the other system left it. But for that, you need persistence, and you need some kind of checkpointing. And to know where the other system left it, so you can take it from there. And this leads us to an extra concept on streaming systems, which is what is the guarantee. So you can imagine if you have you have the possibility of one node which is processing data which is arriving all the time to go down, the best thing you can ensure is at least once, which means if this machine goes down, there's going to be a new machine, but there is a probability that the same message is processed again. So that can be, when you code these kind of things, you have to take this account, because imagine the end point of a pipeline is going to put a transaction for a user in a bank. You have to take into account that transaction can be reprocessed again because of fault of machines. So it wouldn't look very bad if you put the charge twice to the same guy. But there is no way of working around that, because by principle machines can fail. So that's kind of the best thing we can do. If queues are persistent. If queues are not persistent, the best thing you can achieve is at most one, because you cannot come back to it. There's no way of coming back and taking the same data. So between these two, we depend on the brokering system, if it's persistent or not. The last one, which is exactly ones, is even if the systems are advertised that are exactly ones, they are exactly ones, but only for some operations. So if you are trying to keep the sum of clicks for the last hour in a sliding window, there is a way of ensuring that even if I'm going to reprocess the same data, I ignore that sum, and the sum is always correct. But that can only be done for a specific set of operations, and every system complies with, usually the basic ones, like count and sum and these kind of things are usually available. But you can never trust that it's going to be exactly ones for any kind of operation. So you have to design your systems working around that kind of thing, always. And yeah, and an extra thing about this fault tolerance is checkpointing. So we said that we want to give the information in a timely manner. So it is okay that we can come back and reprocess and create the same information again, but you also want to keep the pace. So a way of keeping the pace is checkpointing. If you are keeping some state in the process, so let's say I'm keeping account of the clicks, I don't want to raise a new node and come from the beginning of the stream and wait for it to reprocess. So usually systems have a checkpointing that that state is being checkpointed every X minutes or every X seconds. So when the system goes down and you put a new one, you actually reach the state, and it doesn't need to go to the beginning. So it's actually another concept that is covered by all framework. And the last kind of dimension of these streaming systems is the delivery model. So when we're getting these huge amounts of data, we can, maybe our system needs for every message to be processed once it comes and just flow through a pipeline until it is processed, or maybe we're only doing aggregations. So systems are, they call it one at a time. So there are systems that are one at a time that allow you to process message by message, one by one. And those systems are usually very good for getting the quickest response for one message, for each of the messages. And there are systems that on top of that allow micro batching. So if I want to have a sliding window, I will do batch of a window of the last hour, and I will be moving that sliding window and getting rid of the data I need. So they will cope with that transparently. And there are systems like Spark that actually they only do micro batching, which is kind of a difficulty because they will never reach the performance of a one at a time if you need it. Because you will always need to wait for a micro batch to accumulate to start doing something with it. So, first part of the architecture here, we're going to talk about the gathering and brokering with Kafka. So, putting all together now is going to be very quick. So we have different machines or different people or different iPhones or different whatever, and they are producing data, and we're going to be doing streaming of that data. So we just translate that in the terminology that Kafka uses for the model, after the model I put before, is the sync, they call it topic. Partition key, you have to decide a partition key, so maybe it can be the user profile ID. And data, let's say it is the page the guy is clicking. So each of the phones just takes the partition key and does a small calculation in the phone. It says, okay, the hash model, the number of machines, and they just talk to the data machine and they just send that. And all the data keeps accumulating in partitions of different topics. So we play with the partition key to do the system. So we use the partition key to put the data that we want, that we're going to use in the rest of the pipeline in the most efficient way. So we get to choose that ourselves. In the other side, we have consumer groups. So consumer groups, if you're going to parallelize a topic, and maybe we'll have 100 shards of it or 100 partitions, that's how they call it in Kafka. We can say, okay, we have a consumer and it's taking from all the partitions, but that's not going to scale. There will be a point where the thing will have a bottleneck. So what they actually do is they use a coordinator system. I think Kafka is zookeeper, so they keep a coordination. So I say, I'm going to read partitions. So if you set up different machines that pertain to the same group, first thing they do, they talk to the coordination system and say there is any other consumer consuming from this topic, and they say, okay, and they will take the partitions that are left over, or they will split the job between different machines. So in order to scale up the consuming of a Kafka queue, you just need to put new consumers that are pertaining to the same group, and they will start splitting the task between them. So if you raise in the previous slide, okay, in this slide we have consumer one, and we say, okay, I raise a new machine, there is a new consumer, it will coordinate with the other one, and we will start dividing all the partitions. And we can just keep doing this, this, and this. But there is a limit on the number of partitions you have decided for the topic, so you cannot have more consumers than partitions, but because that wouldn't make sense. So this is very abstract, so I would like to give you a hint on how does this look like in code. So we have a small and you will actually realize it's actually presentation mode. Okay. So how does the producer look like? So as you can imagine, there is a library, Kafka client, that you just put it in your language of choice. This is not in the right place. Let's move it. Here. Yeah. So I'm going to show a small example in Java, but it is clients for Scala, for Python. I think that all major languages are covered. So how does it look like? So basically we have a Kafka producer, which is going to create a key and a message. In this case, it's very simple. The key is going to be just an integer, and the message is going to be just a character stream. So we first have to configure. Usually, what we have to do first, we have to configure who are they going to talk to. So things we have to configure. We have to tell them how to serialize the key that is going to use to go to the partitions. You have to tell him how do you serialize the data, and you can see that you can even implement your own serializer. So the system is only going to, the Kafka is only going to deal with the brokering. It doesn't impose any kind of serialization, so you can use anything there. And you get to decide what is the partitioner. Actually, I think even here, I just implemented my own serializers and my own partitioners just to play around. So the partitioner is going to do this process of how do you use the hashing to send things to machine. So you can even tune that yourself to decide how things are partitioned. The next thing you have to set, so if you have in a Kafka cluster, you have like 20 machines. For resilience, you just need to be able to connect to one or to one of them to be able to read the metadata and know all the IPs of everybody and know how to talk to the system. So that's the last part we have here, which is the bootstrap service, which is saying what is the URL and port of a set of servers that I can talk to, so I can start playing. The last bit, how do you produce data? So in this case, it's very simple. I just randomly assign a key. So basically, it's just a no-brainer. It's a one-liner. Once you have configured the producer will start a session talking to the cluster and will say, okay, I will wait here for you to produce data. And then you just say produce send. And you just wrap the key value that you want to send in this abstraction, which is the envelope that is going to allow him to partition things and share them. So if we try this out, does someone know how to do the mirror? Because it's going to be very difficult to finish the talk like that in Mac. It's a small question. Do you know how to do the mirror of the screens? So a small note on how did you set up these things. So as you can imagine, the operations of this is a bit of a mess. So you have to have a cluster. In this case, everything is simulated in just one node. But you can imagine if you want to deploy this in variable OS on your own machines, you have to have a set of clusters, and you have to be able to just root SSH all of them. And once you are able to do that, there is a manager, like for example, with a Hortonworks SDP that allows you just install everything and coordinate everything, because there is a lot of configuration going on. But this embody that we're having a look is actually the coordinator for everything, so I will be able to coordinate a cluster of machines from here. So you can see that in this system we have HDFS, which is a file system, and one of the bits we have is the Kafka system, that is the queue I was describing to, and the queue we're going to produce data to. So there is a small tool called Kafka Manager, which is just a web page that you connect to the cluster. It's actually very useful and allows you to see what's going on in the cluster. So if we just go to, what's the name of this one? It's Kafka Message App. Playground. So if we start producing, we're going to produce some random data in the file system, so we are able to have something to produce to that, to send to. So at this point, we're just creating some files here with data on it. So this is increasing, and this is a stream of data, a sample stream of data that is creating on this file. So this will be the gathering part that I want to send to the brokering system, so it can be used for other systems. So if we run the producer, which is just the piece of code I showed you before, which is basically 10 lines of code. So you see what's happening? So basically just going to this folder, and all the files that are being created is just pushing them. So what it's actually doing is it first starting the session as we saw with Kafka, and now every time it has to send a message, it just creates a send. So if we go to the manager, we will see that there's a topic there which is calling mail. That's where all the messages are coming in. We can see that it has one partition because that's the one it has from default, but let's try to play around with it a little bit, and let's increase the number of partitions of it. So you can see that everything is happening without having to stop any system. So basically just change the metadata, but nothing actually needs to be stopped to be configuring this kind of thing. So you face a situation where you're producing data and you are not able to keep the pace. You just from the manager just configure it, and things start to be shared to different machines, and the thing keeps going on. So we have 3 partitions now, and you can see that the system started to produce data to different partitions just transparently. So what happens if we want to start consuming from this? So let's have a look to the consumer code. So consumer code is the parallel bit. You have to use basically the same key deserializer and value deserializer you use for the producing. So you have to keep those 2 things in sync. And you have to declare a group ID. So you have to declare this consumer, which group this consumer belongs to. It can belong to a group where he is the only consumer, or you can start increasing the number of consumers for the same group, so you start parallelizing the process as you grow the number of partitions. And consuming is, the bit of code you need for consuming is quite simple, so you basically poll the system continuously. So this is going to poll the partitions it has been assigned to for new data. So if we go run this, sorry, consumer. We're saying random class, and from this topic, from the topic mail, start from the earliest. So this is a configurable thing which is very useful and actually tells with the Kafka architecture. So you can choose with a persistent queue, you can choose whether to start from the beginning or start from the last. And with that, you can start playing. So if I'm creating a pipeline that starts from now, I will just say, okay, start from the latest data, and I just keep going. But if you are reprocessing because you have changed the code base, you actually put things in the queue and say, okay, start from the beginning, from the earliest, because I want to reprocess everything. So the only change you have to do in the code you're deploying is just saying from the outside, start from the beginning or start from the end. So you can see this thing started consuming from it. And if we go to the manager, we will hopefully see. Yeah, unfortunately, we cannot see the consumer because the web is not working very well. But we can play around with it. So we have said, okay, there is 3 partitions of this topic, and there's only one guy. So actually, at this point, he's taking everything. So if it was 100 machines, he will be the only one who is actually working, and that could be a problem. But if we actually keep going and say, okay, I just run the same process again. Oh, sorry. You can see there has something happened here. Yeah, something happens here. So he just first went to the coordinator, which is the zookeeper, and read what's going on, and they said, oh, there's one guy in this group, so we have to rebalance. So this guy was saying, okay, he was notified, it's going to be a rebalance. They just organize and say, okay, there's 3 partitions, you're going to take 1, I'm going to take 2, and at some point everything just keeps going, and we have now a parallel system that is consuming for different partitions from the Kafka without any kind of problem. If we keep, actually, we have 3 partitions, so we can keep going, basically, and new rebalance will happen at some point, because we still have partitions, so we'll say, at some point it will say, still waiting for the balance, and at some point everybody is going to start moving, hopefully. This is moving again, and everybody is moving. And if we just create a new one, what's going to happen is that basically one of them is going to be stalled because there's only 3 partitions, so there is no more parallelism that can be achieved from this topic. If you want more parallelism, you have to basically increase the number of partitions, so the data is more split into more partitions, and the consumers will start consuming from each of the partitions. So this is moving, so one of them is stalled there. But this seems quite manual, so I have to manually create those processes to be able to coordinate everything. So that's not a good way of going. But even if it seems so very dumb, that's what it is. There is no more trick on that. So for achieving parallelism, that's the procedure is using. So now everything we put on top is wrappers for not having to do these kind of things manually. But what's going to happen behind the scenes is the same thing. So what framework do we have available for doing this part, the processing part? So turns out, as I said, there are a lot of frameworks, and all of them use different terminologies, but they basically have more or less this. They can be classified by the dimensions we said before. So we have a Storm, a Spark Streaming, Flink. Well, we'll probably have more, but those are the ones I've reviewed. Storm, Spark Streaming, Flink, SAMSA, Dataflow from Google, and Kinesis from AWS. So as you can see, major things that can be seen from this table is that out of all of them, even if it is one of the most popular, Spark Streaming is the only one who doesn't achieve, who cannot do one at a time. The model is, because the model is based on RDDs, and RDDs are sets of data, they have to actually have a set of data to be able to process data. So it is impossible in this framework to do any kind of one at a time. Storm is the oldest one, is the first streaming system that goes out there, and is kind of trying to catch up with the new systems, because new systems just born with all the experience that happened before. So they are better built, but it's kind of catching up thanks to this Trident library that they build on top of it. Deployment, there's not much difference in deployment. So the proprietary ones, they can only be deployed on the infrastructure of the owner of it. So Dataflow can only be deployed in Google, and Kinesis can only be deployed in AWS. But it seems that for the rest of the systems, Yarn is kind of becoming the standard. So Yarn is just a system that provides you with a computer. If you have a cluster of machines, it just manages the hardware. And so you can ask for 2 processors and 1 gigabyte of memory, and he will assign you these 2 processors and 1 gigabyte in some of the machines it is managing. So the framework does not have to cope with that. It's already abstracted on the layer. So it seems that Yarn is the standard on that. Pretty much, so Storm, so when it comes to windowing, which is just, I want to have the count for all the users of things that they are consuming in the last hour, this kind of operation. It seems that all of them, Storm, not all of them, but Storm, Spark Streaming, and Flink are actually good at it, but and SAMSA and Kinesis are actually, they don't have, you have to basically do it yourself, and Dataflow actually has coverage for that. If you are more a functional programmer or a procedural or imperative programmer, Spark Streaming and Flink are the most functional ones, and the Storm, when you put Trident on top of it, is kind of functional, and Dataflow is kind of functional, and Kinesis is not functional at all. It's completely procedural. And if I had to choose, what would I say is something that differentiates one framework from the other. So I would say that Spark Streaming has the best machine learning ecosystem for now. So it integrates a lot with a lot of algorithms that they have deployed they have developed in the ecosystem. So that's one thing that is good at it. I would say Flink has the most flexible windowing and the most flexible processing for doing one at a time, micro batching, windowing. It's the most flexible API that you can find with Dataflow. About Dataflow, if you want to reuse the Google ecosystem in the Google Compute Engine, it is a good choice. For example, if you want to use Bigtable that has replication in different countries, just transparent, and that's a good use case for you. Maybe you also go for Dataflow for doing the computing. And Storm has a very original pattern, which is distributed remote procedure call. So basically, you can have a pipeline that is updating data all the time, and you can actually make a call like it was a REST API or a SOAP API for actually getting the last update integrated in the framework that you have to use. I will actually go better for a Spark Streaming connector and using Elastic MapReduce than actually using the Kinesis API, because it is horrible. It doesn't have any kind of functionality. So I had a lot of, if someone wants to go, I think time is short. So If someone wants to go through the examples, I have a lot of examples in each of the frameworks. I will just give an example of Flink one, so we can have a look, but later on I can give examples on all of them. And you actually will have all the codes in GitHub for you to have a use. So how does a code like that looks like in a proper system, not manual, for, let's say, Flink. So, even if it seems daunting and it has seemed very abstract, actually when you see the code, it's actually very simple. It's actually very simple to follow. So this is a Flink example of how to connect to Kafka and do a windowing computation on top of it. So first thing you do, you just connect to the executing environment. This will talk to the jar and say, I will need machines, but I don't know yet how many. But it just opens the connection to the system. Then you just actually, the whole code is actually this bit. So basically, sorry, this is not the one I wanted to use. I wanted to use the Kafka one. So you basically say you have a source of data, and you say I want to have a Kafka consumer and for a specific topic here. So basically, what I did manually before, Flink is going to do it automatically, but it's not to do any kind of black magic. It's just the same thing. It will say, it will go to Kafka and say there is 20 partitions, and it will talk to Jar and say I need 20 guys for you to give me. And once he has the 20 guys, he will just put a consumer for that topic with the same bit of code I just put manually before. Then we do a rebalance because maybe there is some kind of a skew or of data, so it just rebalance the whole set of data is taken up. This is just an example I had for extracting locations from text. Then all this data will come one at a time, so it will read one message from each partition every time a new message is going on. So you can have the option to, once you have read the data, you have the option to repartition it by some property you want to do. So basically here, we want to count the number of times a place has been named. Then for doing the windowing, you just declare, I want to window this stream of data. So I had original stream of data of test. Now I have a stream of data which says this place has been named. Now I want to window that. So I have a sliding time window for the last 5 seconds, and I want you to move that window for 1 second by second. And this thing automatically is going to just keep the data he needs in memory, and is going to big data, and is going to give you every second the last 5 seconds of data that has arrived. And the last thing I said, okay, I want just to zoom the frequency property out of it. So you will keep an updated zoom there. And the last bit, which was the sync, okay, where do we publish it? We could choose to publish to database or whatever. In this example, we say, okay, I want to publish it to another Kafka queue with another topic, output topic, because maybe there is another part of the team which will use that thing for I don't know, for changing the front page or for in real time or whatever. So you can see that actually the basic principles are quite simple. We just been building layers on top of them to make things simpler, so we actually can have a quite complex computation in a functional way in a 20-liner, which is actually quite nice. So I would like to stop the talk there because it will take me maybe another 3 hours to go through all the examples and compare all the code bases. So if you have any questions, I will be very happy to answer. Yeah.
So in the Lambda system, you talked about sort of having a batch and then the streaming, that they were sort of reproducing each other. I remember talking to some company and they were talking about using the batch as a sort of, if you like, update on, sorry, the streaming as an update on the batch. So, you know, they had the batch running, but then somehow the streaming bit is just adding some additional, it's a sort of machine learning context, slant on the, so it's like a differential against the batch rather than an actual system. Is that?
Yeah, I would imagine, for example, if you want to correct that in real time. So imagine you have a base timeline for a user, like in the Shazam news, you have a base news, and you say, okay, this is the base news, but let's say you want to filter out because something happened, I don't know, ISIS went crazy and they killed someone, and maybe a song is not appropriate today. So that would be a situation where I would imagine there is a streaming system that was blocking, for example, news and changing a flag and saying we cannot just publish things, these kind of songs today because something happened. So that's the kind of situation that I would think is kind of a variation of it. But this lambda architecture was thinking more in an historic thing that is invariant. Once you calculated it is not changed. So for example, let's imagine a graph for the stock market. Once you calculate the values, that's it. It won't change. So it's kind of two different use cases, variations of the same use case. But it's just an idea on how to organize things. As I said, I think it's an evolving idea, and probably that use case is going to become so often that they will put a name of it in the end. It's kind of evolving now. I mean, it's just ideas. There's not even frameworks that cover everything. So yeah. So I think there are different systems. I think RabbitMQ has more powerful queuing language, so to speak, so to say. It has more. I mean, the principles in Kafka are very simple, very, very simple. I think RabbitMQ has more. The API is more rich in that sense. From the practical point of view, if you actually go mad, I'm really mad for big, and you want to use a practical mindset, you could say, okay, Kafka has all the toolset now. It was not like that 2 years ago, but I think now it has all the toolset with connections with embodies included in HTTP. So if you want to put a 100-node machine that you have to keep going and it has to perform and you have to monitor and tweak, I will actually go for Kafka because it has a much richer ecosystem in that sense. But yeah, I think that I can imagine a situation where the Kafka language is not enough for you because the checkpointing and the transactionality is not very rich. I think the one in RabbitMQ is richer, but I think that keeping a RabbitMQ cluster is maybe more tricky. That's my feeling. Well, I think Flink is winning now, but I think it has been built from the experience of all of the rest. The first time I saw Flink, I said they're doing the same thing, and I just walked away from the talk. It was last year in London in Strata. Actually, when I was doing this talk, I came back to all the systems and read all the APIs, and I think they just nail it much better than the rest. The problem with the Spark streaming is you will always need to wait for an RDD to accumulate. So you will never have the performance that Flink allows you. But actually, Flink, as you saw it there, it allows you to do the batching too. So what's the reason of using a system that only allows you to do micro batching when you have a system that actually you can choose? And the other major difference I find from Flink and Spark streaming windowing is only based on time. It's only solely based on time. But the Flink one is actually very easy to configure. You can do windowing based on anything, basically. So they have this major difference between processing time, which is the time it arrives, and event time, because if you want to reprocess, you cannot use the processing time, the one, because you are just replaying the stream. You have to use an event time. But it can actually be anything. If you just go to the examples, there is streaming batching based on distance. You just plug in what is the concept of batching for you, which is not that easy in Spark streaming. I think that those are the two major differences between the systems. From the rest, they perform the same. It is functional. They both have Spark and Java, although I think the Spark streaming Java API is horrible, and the one in Flink is quite decent. So from that sense, they're pretty much the same. They deploy to Jan, so I think the two differences are those two.